The Robotic Arm Design Challenge, from computer science through engineering design in New York. So you've probably seen robotic arms in action on assembly lines, in warehouses, or even in space. They're doing work that's repetitive, precise, and sometimes dangerous for humans. In this project, students step into the role of engineers and design their own robotic arm using simple materials like cardboard paired with servo motors and code. The goal is not to build the perfect robot, but to think like an engineer. And here's the core challenge for students. They need to design and build a robotic arm that has at least 3 joints, uses servo motors to automatically move an object from one location to another, point A to point B. The arm has to be functional, stable, and programmable. How they get there is largely up to them, which is where the real learning happens. And this project is built around the informed design cycle, which means students don't just jump in and start building. They clarify the problem, research and explore ideas, generate multiple designs, select an optimal solution, prototype, test, and redesign based on what they learn. What's important to know as a teacher is that the students move through this cycle more than once. The looping back is very intentional. An assessment in this project focuses on the process, not just the final project. Students are evaluated on how they explore alternative designs, how well their servos and code function, and the quality and stability of their build, how they test and evaluate their work, and how thoughtfully they reflect on what they learned. This helps keep the focus on engineering instead of just does it work. But before students ever commit to a final design, they work through a series of knowledge and skill builders, or KSBs. These are short, focused experiences that help students understand how robotic arms move, how different grippers work, and how servos behave, and how to build strong joints out of cardboard. These KSBs dramatically reduce frustration later and lead to much better design decisions. One of the first things students explore is how robotic arms actually move. They look at base rotation, shoulder and elbow movement, and gripper motion. And then they compare those movements to their own arms. This helps ground the project into something that is familiar and gives students a mental model before they ever start building. Students will then learn how servo motors work, both positional and rotational. They'll experiment with angles, speed, and direction. They will see what happens when things move too fast or beyond their limits. And this is important because later, when something doesn't work, students can help diagnose whether the issue is mechanical or whether it's related to the code. And a key engineering concept that this project is that students must generate more than one design idea. They sketch different arm layouts, try different gripper concepts, and think about different servo placements. If there's only one design, there's no way to choose the best one. And engineering is all about making informed choices. When students have multiple ideas, they compare them to using specific criteria. They consider things like strength, stability, range of motion, feasibility of materials, and whether or not the design can realistically complete the task. The goal here isn't perfection. It's choosing the best compromise based on the evidence and reasoning. And when students move into building, they do it in stages. They construct the base, make sure it works. Then the upper arm, then the lower arm, and the gripper, testing each section as they go. This staged approach prevents small problems from becoming big ones later on and reinforces the idea that testing should happen continuously. Speaking of testing, testing and evaluation are always tied back to the original specifications. Students ask questions like, does the arm run smoothly? Can it reliably pick up and move objects? And does the code run consistently? The results of these tests guide what needs to change next. And redesign is not optional. It's very expected and encouraged. Students identify weak joints, adjust servo placement, maybe reinforce some structures, or rethink their gripper design. This is where a lot of the deepest learning happens because students are applying what they've already discovered and tried. And at the end of the project, students reflect on what they've learned. They think about the engineering challenges they faced, how their coding evolved, and what trade-offs they had to make. And then what would they do differently next time? This step helps solidify the learning and makes learning process explicit. And if you want to extend the project, there are plenty of options. Students might add some sensors for automation, improve the difficulty of the task, improve the precision, or apply a real-world constraint. These extensions allow the project to scale for different grade levels or time frames.